Howdy folks. Welcome to another solution for Ted Shifrin's Multivariable Mathematics. We're looking at problem 1.3.3, which is just chapter 1, section 3, problem 3. We're asked to suppose that you have these vectors x, v1, v2, v3, all the way up to vk that are in Rn. And suppose that x is orthogonal to each of these vectors v1 through vk. Basically just saying that if you ever took a x dotted with any of the v's, so x dot vi, you could be sure that their dot product is 0. That's what that means. So what we want to show is that this then implies that x is orthogonal to any linear combination of these vectors. Okay, so let's go ahead and show that. Proof. Okay, so this is going to be a kind of nice tight one-liner. So what I want to show is that x is orthogonal to this. So, how would I show that? Well, like I just said, being orthogonal means your dot product is 0. So the first thing I should do is go check what the dot product is. Let me see what the dot product is. So x dotted with this linear combination, which I'll write a little more compactly with summation notation, okay, so I've got the dot product, and I'm hoping, fingers crossed, that this is going to come out to 0. Well, remember, the dot product distributes over the sum. So this is really going to be the sum from I equals 1 to k of x dotted with c sub I, v sub I, right? But then remember, I can pull out the coefficient here, the scalar value here, right, for the field element, right, that I'm multiplying by, and look at it as this times the dot product here, right? So this is equal to the sum from I equals 1 to k of the coefficient ci times x dotted with vi. But wait a second, we already know that individually x dotted with any of these vectors individually is 0. So this is just ci times 0, and you're summing it all up. It's just a bunch of zeros. So it's just 0. So yeah, these are orthogonal. All right, that's it. That's the proof. Hope you enjoyed it. I'll see you next time.